Today we will talk about limits. This is section 10.1. Introduction. The mathematics of change is largely about the rate of change, how fast and in which direction the change is occurring. Calculus provides a systematic and a straightforward way of calculating rates of change. Credit for the invention of calculus is given to two mathematicians, Isaac Newton and Gottfried Leibniz. Newton, an English mathematician and scientist, developed calculus first, probably in the 1660s. Limits are the most fundamental ingredients of calculus because we use them to define differentiation and integration, which are the main branches of calculus. Definition of limits. If f of x approaches the number L as x approaches a from both sides, then we say that f of x approaches L as x approaches a. And then we write that in a compact notation. Limit, we just write it LIM for limit. LIM f of x as x goes to a is equal to L. Evaluating limits numerically. To evaluate limits numerically is to evaluate limit using a table of values. So we will evaluate a limit of x plus 2 as x approaches 3. So here we will consider values closer to 3 but not exactly at 3 from the left. So these values would be 2.9, and then we go much closer to 3, we go to 2.999, and then we go to 2.93 times, and then 2.94 times. And then we plug these numbers into the function, and then we get 4.9, 4.999 up to 4.99994 times. So we see that the first number is closer to 5, but the last number is much closer to 5. And then we said, well, the limit of the function as x approaches 3 from the left is equal to 5. By estimation, we just do some estimation. Again, we consider numbers that are closer to 3 but not quite at 3 from the right. And these numbers would be, these numbers are in column number 3. So these numbers would be 3.1, 3.01, 3.001, 3.0001, and then we plug those into the equation x plus 2, and we get values for f of x, which are 5.1, 5.01, 5.001, and 5.04 times 1. From the table we see that the values of the function f of x are approaching x from both sides, are approaching 5 from both sides as x get closer to 3. And then we just say, okay, well, based on the on what the table suggests, we say the limit of x plus 2 as x get closer to 3 is equal to 5. Again, in this example, they ask you to find the limit of 1 over x squared as x get closer to 0 or x approaches 0. Again, we construct a table that consists of four different columns. So column number 1, we consider values that are closer to 0 from the left but not quite at 0. And then on the third column we consider values that are closer to 0 from the right but not quite a 0. And then when we plug these numbers into the equation, we get the first number is 100. The second number that we find is 10,000, a million, 100 million. So these are very big numbers. So the closer we get to 0, the bigger the numbers become. So then we say the limit of the function is equal to infinity, because the numbers increases without bound. In this example, as we continue on evaluating limits numerically, we want to find the limit of the function absolute value of x over x as x get closer to 0. So first we find the right hand limit, and then we find the left hand limit. The right hand limit suggests that the limit is equal to 1. The left hand limit suggests the limit is equal to -1. Right hand limit is not equal to left hand limit. Then the limit of absolute value of x over x does not exist, and we write D and E. Evaluating limits numerically. So if they ask you to evaluate limit as x goes to 9 of x minus 9 divided by square root of x minus 3. Again, we construct a table. We pick numbers closer to 9 as we are approaching it from the left, and these numbers would be 8.9, 8.999, 8.999, and we plug those into the equation, and we find 5.98329. And if the second one, when we plug 8.999, we find 5.99833, and when we plug 8.999, we find 5.9983. And if we observe these numbers, we can estimate these numbers are approaching 6. So we say the left hand limit is equal to 6. And when we plug numbers like 9.1, 9.01, 9.001, also we get numbers that are closer to 6. Then right hand limit is equal to left hand limit, so we conclude that the limit of the function is equal to 6. So what we discussed so far is evaluating limits numerically. Now let's start with finding the limits using a graph. So if they ask you to find the limit of a function x squared minus 1 divided by x minus 1 as x approaches 1, so we graph this. When we graph it, we see the graph below. So the graph below suggests that as I'm getting closer to 1, the values of the function from the right and from the left are equal to 2. So then we say, well, the function tend to be 2 at that point, then the limit of the function is equal to 2. Evaluating limits graphically. So also we can graph the function absolute value of x over x. When we graph it, we see or we find the below graph, which suggests that the right hand limit is equal to 1, left hand limit is equal to -1. So right hand limit does not equal to left hand limit. That means limit does not exist. So we will talk about limits and continuity. So how we can use limits to evaluate the continuity and discontinuity of a function. If the graph of a function may be drawn without lifting the pencil or pen from the page, the graph and thus the function are said to be continuous. So on the left we see a continuous function. So f of x is continuous at x equal to c. That means the limit of the function at point c is equal to the function value. A break in the graph, such as at x equal to c, is called a discontinuity. So if you see the picture below, you'll find that the limit of the function does not exist because we have jump discontinuity. Continuity at a point. Assume that f of x is defined on an open interval containing x equal to c. Then f is continuous at x equal to c if limit of f of x as x goes to c is equal to f of c. If the limit does not exist, or if it exists but is not equal to f of c, we say that f has a discontinuity, or is discontinuous at x equal to c. If a continuous function is defined on a and b, and c is any point on a and b, then the following condition exists. The right hand limit of f of x equal to f of a. Left hand limit of f of x equal to f of b, and limit of f of x equal to f of c for all c on the closed interval. A jump discontinuity may be one-sided continuous as shown over there. An infinite discontinuity is one in which one or both one-sided limits are infinite. Since infinity is a concept rather than an actual number, f of 2 is not defined in figure A or B. Evaluating limits algebraically. 10.3. How to evaluate limits algebraically. If the function f of x is continuous at x equal to a, then the limit of the function f of x as x goes to a is equal to the function value f of a. However, we may be faced with limit of f of x where f of a is undefined. In this case, we can evaluate the function using substitution, provided we first use algebra to rewrite the function. Indeterminate forms. In general, we say that f of x has an indeterminate forms at x equal to a if f of x is evaluated at x equal to a, we obtain an undefined expression of the type 0 over 0, infinity over infinity, infinity times 0, infinity minus infinity. Evaluating the limits algebraically. If you have limit as x goes to 2 of x cubed minus 8 over x minus 2, first we do the substitution. We substitute for x equal to 2 and we get 0 over 0. The quantity 0 over 0 is indeterminate form. Then we use factoring techniques. So when we factor x cubed minus 3, this becomes x minus 2 times x squared plus 2x plus 4 divided by x minus 2. And then we cancel out x minus 2. It's a common factor in the numerator as well as in the denominator. And then we do the substitution and we find the answer to be 12. So every time we do substitution and we find indeterminate form, we use factoring techniques, or we use any other appropriate algebraic approach to change the function or to come up with an equivalent function. For instance, if they ask you to find limit of x cubed minus 1 over x minus 1, so we factor x cubed minus 1 into x minus 1 times x squared plus x plus 1 over x minus 1. And then we get x squared plus x plus 1. And then using a substitution method, we get 3. So we do also evaluate limits algebraically as follows. If they ask you to find limit of x squared minus 16 over x minus 4, first we substitute x equal to 4, so we get 0 over 0, and then we use difference of squares, so then we have x minus 4 times x plus 4 over x minus 4. So we cancel out the common factor, and we have a new function which is x plus 4, and when we substitute for x equal to 4, we get 8. Evaluating limits algebraically. Evaluate limit as x goes to 4 of a square root of x minus 2 divided by x minus 4. First, substitute x equal to 4 into the function square root of x minus 2 over x minus 4. If we do the substitution, we obtain 0 over 0. This is indeterminate form. And once we have indeterminate forms, we will think of an algebraic approach that will alter the function. And since the function involved radicals, the best approach usually is to find the conjugate. So now we will find a conjugate of square root of x minus 2. And the conjugate of that would be square root of x plus 2. So we multiply the numerator by square root of x plus 2 and the denominator by square root of x plus 2. So if we multiply both up and down, we can we find, so the square root of x minus 2 times the square root of x plus 2 become x minus 4 divided by x minus 4 times square root of x plus 2. So x minus 4 cancel out. Now the limit of the function as x goes to 4 is 1 over 4.